So welcome back, Lecture 20, Math 141. We are now into Chapter 3, which has shortcuts of the derivative, so we're all happy about that. We're going to have time, I think, at the end of class today for some WebAssign questions. Apparently there's one that is giving people grief, so we'll try to see what's going on there. Today we're going to do the product rule. So when we have, instead of like x to a power or a coefficient times x to a power, we're going to have the product of two functions, and to avoid multiplying them out before we find the derivative, we've got a rule. So I know a lot of you have had some calculus, you're well aware of that, but let's validate that it in fact works. We'll also have a similar rule for the product of two functions, for the quotient of two functions. So a product rule and a quotient rule. So let's kind of develop them here first, both of them, and then we'll look at some relevant examples, and then we'll, time permitting, be able to look at some of those WebAssign questions as well. So this is Chapter 3, Section 2. Product rule for finding first derivative. And the quotient rule. So let's start with product rule. When we don't have a rule, what we do pretty much in every circumstance is we go back to the definition. So let's say we have some capital F of x is the product of two functions of x. So we've got some binomial times some trinomial. We've got a product, an indicated product. So what we want to try to do is avoid multiplying it all out before we take the derivative. So the derivative, by definition, so we want this product function evaluated at x plus h, which would be f of x plus h times g of x plus h. So we put an x plus h there and there. From that, we want to subtract the function at x. All over h as h approaches 0. Does that look like the definition of derivative? Product function at x plus h minus the product function at x all over h as h approaches 0. All right, let's keep this term where it is. I'm going to subtract a term. So I'm just putting that in there. Now, if I subtract that term, that's not up here in this original numerator. It's legal to subtract something as long as you also add it back in. Is that correct? So I'm going to subtract f of x plus h times g of x. I'm going to also add that, which might seem not so smart. So all that over h as h approaches 0. Now we're going to split this up into two pieces, and if some of you already know the product rule, you know that we're going to get two parts to this. So I'm going to take the first two terms, so this thing that I kind of manufactured, and I'm going to go ahead and write that over h and let h approach 0. So I'm taking this piece minus this piece over h. And then we've got these last two pieces now, f of x plus h, g of x minus f of x. Does that seem legal? I could write all four of them over h. Is that correct? Because I've got a sum and difference in the numerator, so I could write this over h, this over h, this over h, and this over h. But I'm going to take them in pairs. Hopefully it might be a little evident at this point why we want the pairing the way it is. Do you see anything in this first one that we could do that would factor something out in front?
Allowed in f of x plus h.
The two terms in the numerator have f of x plus h. Is that correct? So let's factor that out in front. And when we do that, what's left? G of x plus h. We factored that out, so minus g of x. All over h. Is that all right? So we took f of x plus h out of here and here. Factored it out in front. From the second one, do you see anything that we could factor out in front?
G of x.
G of x. There's a g of x here and a g of x here. Let's factor that out in front. When we do that, it leaves f of x plus h minus f of x. Now, as h approaches 0, do you see anything in that first, in this one, that looks at all familiar?
G of x plus h.
What does this sound like to you? G of x plus h minus g of x all over h as h approaches 0.
The derivative of g of x.
That's the derivative of g. Is that true? This part that I'm going to circle is really g prime by definition. Now, what happens to this thing that we factored out in front as h approaches 0? What happens to f of x plus h as h approaches 0?
Goes 0.
Well, if h approaches 0, that's just f of x, right? So the first one is a little bit uglier than the second one. But at this point, we have f of x times g prime. What about this circled quantity right here?
Derivative of f.
That's derivative of f. And we don't have to do that same thing out in front. We've got g of x times f prime of x. So what we have, there's f of x. That h went to 0, so it's times g prime plus this g of x. We don't have to do anything at all with that except write it down. And this circled quantity is by definition f prime. So there is our capital f of x derivative. Does that look familiar? If you've seen product rule before, take the first function times the derivative of the second plus, which means you can commute this order, doesn't matter. Addition is commutative. Second function times derivative of first. So if that's the first time you've seen the product rule, or even if you've seen it before and it's been a while, make sure you have that jotted down. So that's our shortcut that we're going to call the product rule. Now, we'll get some examples of that in a second. Let's get the quotient rule, and then we'll get examples of both of them. Any question on the development of?
There's 3 of them, like f of x times g of x times h of x. Does it work the same?
That's a good question. Let's see. We're not going to go all the way back to the definition, but let's see if we can use what we have to this point to see what that would be. So let's say that our capital F of x is now don't confuse that h with the h that we allowed to approach 0, the little delta x increment. So we have 3 terms in our product, so we can possibly see a pattern here that would work for We've already seen it for two terms, but it may not be as evident as it becomes when we do this. Let's call the first term the product of the first two, when first time through. So here's our first term. Here's our second term. So the derivative ought to be first. There's the first. Times derivative of second plus second times derivative of Does that work? It's going to simplify, and then you'll see a pattern, and you can use that pattern for multiple products. So I'm going to leave that one alone. Now we've got a little bit of work to do here because we have the derivative of the first. Well, the first happens to be what? A product. So in order to derive the first, we have to use the product rule. So that would be first times, that's not first. This is commutative, right? So I'm going to invoke that right now so I don't have to try to get rid of that. So derivative of first times second plus what? Derivative of second times first. That's not exactly the way we did it, but it is commutative, so that ought to work. So we've got FG times derivative of H. Let's distribute the H here. I'm going to put it in an order where hopefully it will GH times derivative of F, and then distribute this H to this term, and that ought to be FH times derivative of G. So do you see a pattern there for three terms in the product? The product of the first two times derivative of the third, product of the second and third times the derivative of the first, product of the first and third times derivative of the second, right? So it's the product of two of them times the derivative of the other one. Any guesses what that would be if there were four terms in the product rule?
Just put down the line product.
Product of three of them times derivative of the fourth, and kind of keep going until you've exhausted that whole pattern as well. So that's a three-term product rule. Probably more than you wanted with the question. All right, quotient rule. So let's see if we can use the product rule to help us develop the rule for finding the derivative of a quotient. And I don't know if this is the one that's used in this book. You can go all the way back to the definition, but since we have a rule that can help us, I figure we might as well use it. So I've got this quotient, but I want to rewrite this statement in terms of a product so we can use the product rule. How can we accomplish that? Do what? I want to change this into a product. Multiply both sides by g of x. So if we do that, those knock out. We are trying to find the derivative of capital F prime. So we have little f of x by itself on the right side, and the left side, as I write it this time, is their product. So we started with a quotient, multiplied both sides by g of x. Now we have a product. Keep in mind what we want. We want f, capital F prime. So let's take the derivative. Derivative of the left side, that's easy, f, little f prime. The right side is a product. So tell me what to write down for the derivative of that product.
G of x times derivative of f
Okay, capital F prime.
plus
G prime.
yes.
Is that right? For the product rule on the right side? And what do we want to find?
F prime.
We want capital F prime, right? So let's see if we can solve for capital F prime. So let's leave this term here. Let's move this term to the other side. So if we move this term to the other side, it's going to be negative. All right, we're trying to solve for capital F prime. What's next?
Divide by G.
Divide by G of x. Now, some of you already know the quotient rule. That's not it yet. What can we put in here? We want capital F prime. We don't want capital F in there. What is capital F equal to? All the way back to when we started.
F of x over G of x.
This, we can make a substitution. And that's going to be f of x over g of x. It's getting closer. What will take this, which is pretty close to the so-called quotient rule, what will take this version and make it the quotient rule?
Put the G of x in the bottom.
Well, I could do that if I could also do that here. By the way, notice there's a minus sign, which tells us that it's not commutative, right? So order is important here. Product rule, you can start it either way because it's
Multiply
Everything by G of x.
good. Multiply everything by g of x. Multiply the top by g of x. And multiply the bottom by g of x. So what does that become? That becomes f prime g of x. This g of x and this g of x knock each other out, so we've got f g prime. Down here we've got g of x times g of x. Now, I think I'll rewrite that one more time. That's very, very close to probably how you want to use it. I'm going to start with the g of x. I'm just going to commute that order in that product. G of x times f prime minus, that's important, f of x times g prime so that's our capital F prime. So there is the quotient rule. That's actually a little cleaner, a little quicker than going all the way back to the definition. All right, now let's put that in words. Okay, let's go back to our original problem, our original capital F of x was that quotient. So in terms of that original quotient, describe to me how this goes.
The
Denominator
times the derivative of the numerator
times derivative of numerator.
minus the numerator times the derivative of the denominator all over the denominator squared.
Okay? Everybody catch that? Especially if it's the first time you're seeing and using the quotient rule. And I know if it is the first time, you're thinking, I'll never be able to learn that. You'll be surprised. You'll probably know it by the end of class today. But the order is important. because it is subtraction. So start with the denominator. That was the denominator. Denominator times derivative of numerator minus numerator times derivative of denominator all over the original denominator squared. So there's our quotient rule. Ken.
Something my teacher taught me to make it a little bit easier.
Okay.
If you think f of x is high and g of x as ho, the quotient rule is ho d high minus high d ho over ho ho.
That's a little too sing-songy for me.
I know. she made a song, like a 3-minute song about it.
So this is
And it worked.
ho d high
Minus high d ho.
minus high. That's a. You're
That's
gonna
a
start
lot.
breaking me into song.
I do the
High d ho all over ho squared.
Uh-huh.
Okay. I like it, but I'm not gonna use it personally.
It helped work.
Yes.
I do the u prime v minus uv prime over v squared. Like you think of f of x as u and
U over v.
yeah.
Okay.
Well,
So-
a lot easier than the g of x.
So v. So you want denominator, right? U over v.
I just do like
U and V values.
if f of x was u and g of x was v, it'd be u prime v.
Oh, okay. So this is u,
Right.
and this is
And
v.
that's v, yeah.
So u prime
v
v
minus u v prime
minus u v prime all over
v squared.
v squared. That'll work. Both those work. You got another one, Blair?
Well, I just wanted to ask you about this. I've used it sometimes. Depending on the equation, this makes it a little bit easier. Could you rewrite f of x over g of x as f of x times g to the negative 1x,
That'll work.
Sometimes that's
and then use the
rule.
product rule?
Yes, that would work too.
Okay.
And some problems, it's not as many as you might think. That might be the best approach. But, I mean, this isn't that bad. I mean, if you're seeing it for the first time, you're thinking, oh, my goodness, I just can't do it. But you'll be using the quotient rule successfully here in just a couple minutes. Anything else about product and or quotient? Which also goes the other way. If you see something that looks like it could become a quotient really easily, and you think that might be a little quicker than the product rule, that works too. If you have something to the negative first, throw it down to the denominator. All right, examples. So let's see if we can use this smart board or see if it's still smarter than I am. All right, product rule. So let's say, and let's keep the first one pretty simple, I'd like to do one that we can use the product rule on and then not use the product rule, check it by methods that we already have prior to what we're doing today. X plus 4, 3x minus 5. So product rule, somebody take over from there now that you're all experts.
X plus 4
How would that go? X plus 4.
times
3.
3.
Okay, derivative of the second is 3
Yep.
plus
3x minus 5
second, 3x minus 5
times 1.
times derivative of the first, which is 1. Everybody okay with that? And then multiply it out and simplify and see what we get. So 3x plus 12 plus 3x minus 5. So the derivative is what?
6x plus 7.
6x plus 7? So how can we check that?
Multiply off the thing.
Okay, let's multiply the top, x plus 4 times 3x minus 5, use the power rule, which we already had, and see if we don't get the same answer. So same original problem. Plus 4, 3x minus 5. Before we take the derivative, let's multiply it out, which is going to be what? 3x squared.
Plus 7x.
There's 12x, and there's minus 5x. Plus 7x?
Minus 20.
Minus 20?
It's going to become the same.
Now, we're not going to have the luxury of checking all the time, but we can check here. Derivative of 3x squared, 6x. Derivative of 7x,
7.
plus 7. Derivative of minus 20
0.
is 0. Same answer?
Yes, sir.
Same answer. All right, let's try another one. So let's say the original function is x squared times e to the x. So we do have a product. All right, how does that go?
X squared
X squared
times e to the x.
times derivative of e to the x. I think we got that last class, right? One of the easier ones
E to the x.
is its derivative is itself. So that's first times derivative of second plus
2x.
second
E to the x.
times derivative of first, which is
2x.
2x. Now, depending on what you're going to do with this derivative, right now we're kind of finding them, and we're not doing a whole lot with them. We have some kind of low-level applications. But you might want to factor some things out in front, especially if we're going to set it equal to 0. That might be helpful.
E to the x and x.
What can we factor out in front?
E to the x.
E to the x and
And
also
X.
x. So if we factor those two out in front, what's left in the first term?
X
X.
plus 2.
X. And what's left in the
X.
second term? So I don't know if that's real evident, but if we were taking the derivative and setting it equal to 0, that would be easier in this form than it is, what in the world? Easier in this form than it would be in this form, right? Because you could set x equal to 0, you could set e to the x equal to 0, and you could set x plus 2 equals 0. Not that we're going to do that all the time, but we will be doing that some. Blair,
Have we learned chain rule yet?
we have not.
Okay. Because we did either e to the x, I just kind of remember that from high school.
Yeah, now that would be helpful if we had e to some other power other than x, like we had e to the x squared plus 2x plus 7, then we'd have to use the chain rule. In fact, if we were setting this equal to 0, what are the solutions? What x values would
Negative
cause
2.
f prime to be 0?
Negative 2.
-2,
And
0.
0, and when is e to the x 0?
1.
1.
When is e to the x equal to 0? It never is, right? So we wouldn't get any solutions from this one. We get a solution x equals 0 here and x equals -2
Does
here.
e to x approach 0 as it approaches negative infinity?
Well, remember what e to the x looks like. It's a graph that looks something like this, right? So it never is 0. It's asymptotic over here to the x-axis, but it never reaches the x-axis. So it never is 0. Okay, quotient rule. And we don't have the luxury to check these. Certainly not as readily as we do with the same two terms. This time they're in a quotient and not in a product. All right, how should that go? Our first go around with the quotient rule. Denominator?
D
times derivative of numerator, which is 1 minus numerator times derivative of denominator, 3,
Square the bottom.
all over the original denominator squared. Is that all right?
Yep.
Proper use of the quotient rule. Now, this is tempting, but don't be tempted by like terms that you see so close to each other. 3x minus 5 and 3x minus 5. In order to reduce something, numerator and denominator, doesn't it have to be present in both terms? There are two terms in the numerator because of this minus sign. This term, which has a 3x minus 5 in it, and this term, which does not. So you can't reduce part of the numerator. You'd have to be able to reduce both terms of the numerator with the denominator. So as tempting as that is, don't reduce those two right there. All right, the numerator. What is everything all multiplied out? What do we get across the top?
3x minus 5.
3x minus 5?
Minus 3x minus 12.
Okay, and remember, everything that follows gets subtracted, right? So minus, what was that product?
3x minus 12.
3x, and then we would have had a 3 times a 4, right?
Right.
And that gets subtracted as well.
Over 3x minus 5 squared.
And in the numerator, what happens?
They cancel out.
Okay, 3x minus 3x. Knock each other out. Minus 5 minus 12. Negative 17. Any questions on that example? So do we know something about this function? I know something about this function because this is its derivative. A negative number, right? There's no variables up there, so it's negative. It's always negative. If we stay away from the bad value in the denominator, something squared is what? Always positive. So this result is always negative, right? Derivative is always negative. What do you think is true about the graph of this function because the derivative is always negative?
It's decreasing.
It's always decreasing. So the fact that this derivative is negative always, that means the entire picture, when you graph it from left to right, will be decreasing. So let's go back to this original function. Any questions about just the use of the quotient rule before we try to make a rough sketch based on what we now know? The derivative is negative. Let's go back to the original function, which is this. Any vertical asymptotes here? Any bad values for x that we have to steer clear of?
5/3.
5/3? Okay, so that'd be a vertical. Any horizontal asymptotes? 1/3, right? It'd be the limit of this as x approaches infinity, so it'd be 1/3. All right, so x equals 5/3, y equals 1/3. So x equals 5/3, y equals 1/3. So there's our two asymptotes. Not very good ones, I'm sorry. What do we know based on the derivative? Where is this graph? The derivative is negative.
Below the.
The only way it could be is right here. Is that correct? It's got to be decreasing? So that's, you read a graph like you're reading a page of print in a book. You read it from left to right. So these derivatives are all negative, right? Negatively sloped tangent lines. We have a little intermission at 5/3, undefined there. And where's the rest of it?
On the bottom.
Up here, because it's got to be decreasing. I think I just hit something that I didn't want to hit. Okay.
Gonna mess it all up.
It's all right. We're going to switch to the paper now for the last example anyway. Now, just because the derivative is negative, we could also determine the intercepts here and here, right? We have a general idea where they are just simply because the curve is decreasing. Had it been increasing, then this curve would have been up here, which would have changed things, right? Drastically. We wouldn't have had an x-intercept here. We wouldn't have had an x-intercept on that particular piece at all. So signs of the first derivative will be important. Before we leave this example, what do you think would have happened had we just changed the order of the terms that we had in the numerator? Instead of denominator times derivative of numerator minus numerator times derivative of denominator, what if we had transposed those? What would our answer have been? Instead of negative 17, it would have been positive 17. And positive 17 over, what was our denominator? 3x minus 5, quantity squared. Is that a big difference? That's just a simple sign error, isn't it? No, that's way bigger than a simple sign error. Because here, we would have the curve with the dotted line here and here, right? Because we would have said the derivative is always positive, therefore the curve is always increasing. So sign errors are not trivial any longer. Sign errors are huge because they're the sign of the derivative, which talks about the slopes of the tangent line. All right, let's do one example, and I think we have a WebAssign. Here's a summary page of the two things that we just learned. For some of you already know it. And then we had a couple of examples on so derivative of a product first times derivative of second plus second times derivative of first plus. So you can commute that order and it's not going to make a difference. Don't commute the order here because it's minus denominator times derivative of numerator minus numerator times derivative of denominator all over the original denominator squared. All right, one last example and then we'll look at a WebAssign question. Find the equation of the tangent line. I think that's the WebAssign question we're going to do too, is similar to that. To this curve. At a specific point, the point being on this curve, 1, comma, e over 2. Equation of the tangent line. What do we need? Derivative, which gives us the slope of the tangent line. So the derivative is slope of the tangent. What is the derivative on this? You see why it is an example problem from this section. How's that go?
5 plus x squared.
1 plus x squared times
E to E.
Derivative of the top, which is e to the x minus
2x.
numerator times derivative of denominator, which I heard, 2x, all over denominator squared. Now you say, well, that's an ugly derivative. And it might be ugly, but all we care about is what is the derivative when x is 1, right? All we're going to do is wherever we see x when we're done, we're going to plug in a 1. I don't know. Anybody see anything major gained by simplifying or distributing and grouping like terms together? I don't see a lot of gain there. We want to know what is the derivative when x is 1, because that's the point we have. The x value is 1. So it is 1 plus 1 squared times e to the 1 minus e to the 1 So what do we get in the numerator? Here is 2e minus what? 2e? What happened there? I guess we lost it all, right? All over 4, which is 0. That makes things a little bit easier. So if the slope of the tangent line is 0, we've got a pretty easy task ahead of us. Y minus the known y value is slope. X minus the known x. Y minus e over 2 is slope. It really doesn't matter what else we write down, right? Because it's 0 times something. X minus 1. So it would be y equals e over 2. So we happen to find the point where the derivative was 0, so it's got a horizontal tangent line. That is a equation of a horizontal line. All right, so that's about the time I anticipated for this, so we do have time to do that one WebAssign question. It's we're talking about 3.1, right? WebAssign question number 10. All right, so somebody read that. Talissa, read that.
Find equations of both lines through the point 2, negative 3 that are tangent to the parabola y equals x squared plus x.
Tangent to the parabola y equals x squared
Plus x.
plus x. Right, now does it say in that problem, which if this was an issue for you, this may be the kind of the thing that sorts it out for you. Does it say that this point is a point on that parabola? And it's not. It's an external point. So let's see if we can get a picture. Not that you need a picture to solve this, but I think it might help decide how we approach this problem. If we were to graph the parabola y equals x squared plus x, couldn't I factor out an x and get x plus 1? Why would I want to do that? Find the intercepts pretty readily. So what x values cause y to be 0?
0, negative 0.
0 causes y to be 0, and 1. Sorry, negative 1, right? Causes y to be 0. So 0, 0, and negative 1, 0. Now, if those 2 points are on this parabola, where is the vertex?
So negative a half.
Negative a half. Doesn't it have to be right in here somewhere? I don't know exactly where it is, but I know if this point is at level 0 and the other point is at level 0, then the vertex is halfway in between there. So the vertex, and you could check that, right? Don't we have a couple ways to find the vertex now? Take the derivative and set it equal to 0. 2x plus 1 equals 0. X equals negative a half. Or what? Negative b over 2a. is the x value of the vertex. You could check it. In either case, you're going to get negative a half. And when x is negative a half, what is the corresponding y value?
It's 1/4.
Negative
1/4 or negative a fourth?
Negative
Negative.
Negative 1/4? All right, so here's our parabola, roughly. And the point is 2, -3. So here's our point, 2, -3. So we're going to have a tangent line that comes up in this direction, right? And is tangent to the curve. And we're going to have another one that is going to come up in this direction. So we're going to have a couple of tangent lines to this parabola. What do we not know? We do not know the points of tangency, right? But isn't it true that the points of tangency have to solve this equation? Isn't that the relationship between x and y of every point on this parabola? All right, let's see what we can come up with. So we know that both of these tangent lines have what for their slope, since they're tangent to this parabola? 2x plus 1. Is that all right? So the slopes of the tangent lines are 2x plus 1. We also know that both of these tangent lines go through the point 2, -3. Let's see what that gives us. So y minus the known y value, so y minus -3 equals slope. We don't know the point of tangency. That's the problem. So I'm going to leave the slope in terms of the x value of the point of tangency. Now, if it bothers you that I'm using x, use another letter. Use a. So the points of tangency are some a value. But there's the slope, and then x minus the known x value, which is 2. Any suggestions or recommendations from this point? Well, we could multiply it out and see what we get. So 2x times x is 2x squared. 1 times x is x. Minus 2 times that is what? And minus 2. So what do we have? 2x squared minus 3x minus 2. And let's just go ahead and solve it for y. Question,
Well,
Chandler?
if you were to use a for the slope, like you know how you said we could use a different,
Right.
how would you multiply that out? Because technically it wouldn't be x squared.
Right. I like this way better because you do have x squareds, and then we're going to use another interrelationship
So it doesn't
of y.
matter.
No.
Okay.
But I'm just saying if it bothered you that I'm leaving that x, then it's kind of an unknown x value is what it is, the point of tangency or points of tangency. All right, so we've got 2x squared minus 3x minus 5. Now, this doesn't look like it, but for the two different x values that are the points of tangency, this is the equation of a line. Now, why does it not look like a linear equation? Because of the x squared, because we didn't know the specific value here. Now, any help getting the points of tangency? Set it equal to 0. So we also know, and we're going to be out of time, but don't we also know this is true?
Are they
Right?
equal to each other?
Oh, plug it in for line. Yeah.
Okay, so if this is true because of the points of tangency, and this is true because of every point on the parabola, and they're both equal to y, can't we set them equal to each other?
Yeah.
Okay, so then you're going to have a quadratic equation which has two solutions. How many points of tangency do we want? We want 2. So take these two and solve them simultaneously. And that's a jump start on that problem. All right, we're out of time. I will see you tomorrow.